Hey, and welcome to the course. So we're going to kick off with Newton's first law. In the video, we're going to introduce Sir Isaac Newton, take a look at his first law, talk about the fixed update loop, and then you'll be updating the transform position of your objects. So there he is, Mr. Isaac Newton. His ideas have been around for about 300 years now, and they've really stood the test of time. So his first law says, when viewed in an inertial frame, an object either remains at rest or continues to move at a constant velocity unless acted on by an external force. I got that from the Wikipedia article, which you could click through to there. So, what is an inertial reference frame? For the moment, let's take the definition as a frame in which you cannot feel any acceleration. So imagine you're out in outer space sitting on a space bench just chilling, and I come accelerating past in my rocket. When I look at you, you'll look like you're accelerating, and when you look at me, I'll look like I'm accelerating. However, if I say to you, hey, can you feel any acceleration? You'll go, no, I'm just chilling on a bench. And if you say to me, can you feel any acceleration? I'll go, yeah, I can. I'm being pushed back in my seat. So therein is the difference in our reference frames. Me, in my accelerating rocket, am not in an inertial frame. You, on your space bench in outer space, are. And we're going to use our game engine's global coordinate system as our reference frame. So let's get this set up as the very first port of call. Here I am in Unity. All I've done so far is created a new project, and I've called it Section 02, and it was a 3D project with no packages. That's got me this far. What I'd also like to do is save the scene as, let's put a new folder in our assets. I'm going to call it _scenes. And then I'm going to call my scene 1 or 01 outer space. Why 01? Well, if I have more than 9, I want them to sort nicely. So here we go, _scene, so it floats to the top, 01 outer space. Beautiful. So we're all saved and ready to go. That's just a blank scene. Now, if you go over to the course at the beginning of the section, I have provided you here with a set of downloads. It should be one of the first few lectures, GP 101 Section 2 assets. When you download that, you will get something looking a bit like this. You'll get a zip file with a folder, and in it you'll have a Unity package. What I want you to do is remember where you keep this Unity package. Just double click on it, and it'll come up trying to import all this stuff by default. Well, let's import none of it except the Stars 1024 skybox for now. And while we're at it, let's have our football texture. So just that lot, the skybox and the texture. We'll import things as we need them. Click import, and we will now have what we need. Another way of doing this is you can go assets, import package, custom package, go and find your Unity package, double click, and you'll notice the list is shorter now. It only shows you the things that haven't already been imported. This is really cool. We can keep track of what we're importing this way. You could just import everything, but the problem is, for one, this draw forces script will not work, and why have all that clutter? Why not just import it as we need it? So what I want to do is set the scene. We're in outer space, so you need to go to your camera and add a component called a skybox. I've actually got two now, so I'm going to remove one of them. Here you go. So in your inspector against your main camera, you have a skybox, and I want you to choose the material as Stars 1024. If you then play the game, and I'm going to maximize on play, you'll see we've just got a star field in the background. That sets the scene. We're in deep space. Nothing is anywhere near us. All those stars are light years away. So effectively have no net gravitational force on us, and there's no other bodies by us. We're right out in the middle of nowhere. Fantastic. So that is setting the scene. This is our inertial frame. So now we need something to play with. Well, let's create ourselves a game object, 3D object, sphere. There he is in the middle of the scene. Now we can't really see that sphere, which is why I've got a football. Click on Assets, Textures, drag the football onto the sphere, and there you go. Finally, we need a light. So let's create ourselves a game object, directional light. Okay, do that. Now the only problem with it being at the origin, the light, is it kind of looks a bit weird because it's coincident with the ball. I want the ball starting at the origin, so I'm going to grab my directional light and I'm going to move it up, let's say 100 units in the Y direction. It's still around, but it's miles above the ball. It doesn't matter where directional lights are in the scene, that has no impact on how they work. So there we are, we have a lit ball. And if we click play now, hopefully you can see a ball with a star field behind it, just sitting there chilling in outer space. Okay, so that's part of the way to obeying Newton's first law. What we need it to do, of course, is we need it to maintain in a constant state of motion. So we need to encode the motion, etc. Let's take a look at how we're going to do that. So, firstly, we're not going to use the update loop. For physics, we're going to use the fixed update loop. That, by default, is called every 20 milliseconds. That's a consistent 50 frames a second, 50 fixed updates a second. And time.delta time returns the current value. It can change while you're using the simulation because you can just choose to go into slow motion, for example. Find out a lot more about it by clicking this link, Unity's Manual on Execution Order. So, the challenge is going to be just to make your ball move. So let's just set some ground rules. The transform.position is what we're going to use for the displacement of the ball from this global origin. So if we look at the sphere here, I'm going to rename it ball and move it under the directional light just for ease of access. There you go, we have a transform position in the inspector. That is going to be its displacement from the global origin. Okay? Secondly, v. We're going to define a variable called v. And we need to be a little bit careful about what v really means, and we'll get into a lot more detail about this later. The computer can never really deal with continuous changes in velocity. It's always going to be taking a snapshot every fixed update. So this v is the average velocity over the last fixed update period, over the last 50th of a second by default. We're also going to have something called delta s, which is the displacement change in this fixed update. And then, of course, distance is speed times time, so change in displacement is the v vector times the time.delta time. So what I want you to do is to define yourself a public variable called v inside a script called physics engine. So let's just put that script on the ball now. New script, physics engine, like that. It needs to be spelled exactly like that, E-N-G-I-N-E, capital P, capital E, because other components are going to require it later. Go into that physics engine script. Make yourself a public, and I'll do this bit for you just so we're totally clear on what I'm talking about, public vector3 v, okay, and let's say what that is. That is the thing that I've said in the slide here. It is the average velocity of this fixed update. I'm going to put that in. Like so, okay? So you defined that. Now the rest is up to you. I want you to set the transform.position of this ball every fixed update to be updated by the current v as per the slide. Okay, so you need to add the method fixed update and put in a simple transform.position plus equals something or other. And the proof of the pudding that you've got it right will be when you come and click ball. Let me just save my script. Remember to always save your script. When you come and click ball, and you set the v here, the velocity, then you will see the position updating. So if you had a 1 in x, then this position in x should be updating by 1 unit every second. If you had a 10, then this should be updating 10 units every second. All right, so it's very, very simple for the moment. So go ahead and do that just very simple challenge right now. Pause the video. Fantastic, welcome back. So this is how I'm doing it. So as I said, I'm not going to use the update loop here in the physics engine. I'm going to be using the fixed update. So I'm going to remove the comment because it's no longer called once per frame. Okay, so I simply want transform.position plus equals, well, what? Well, v, which is the velocity vector. Now, if you don't like v, you can make it much more explicit. So why don't we do that? Why don't we call this velocity vector? How's that? Nice and explicit, times time dot delta time. So every fixed update we are, if we spell velocity vector right, V-E-L-O-C, we are adding to the position an amount of displacement that is the current velocity times the increment, how long we've been going for. So if this delta time is 1 second, we're doing 1 meters per second, we move 1 meter, etc. Simply, distance equals speed times time. Let's just take a look and see if it works. Click play. There's our ball sitting there. I'm going to not maximize on play. There we go. Now, if I give it some velocity in x, look what's happening. Every 1 second, my x position is going up by 1. If I give it a velocity of 10 in y, then every 1 second I get an increase of 1 in x, and I get an increase of 10 in y. Fantastic. So the ball has just gone flying off out of our camera view. And that's great. It now is doing what Newton suggested. If we look back at the slide for Newton's law, it says when viewed in an inertial frame, well, we are, an object either remains at rest or continues to move at constant velocity unless acted on by an external force. Okay, well, the last bit we're going to deal with in the next video, but for now what we want to do is just make our camera follow this guy. So again, I've provided you with a script for that. Import package, custom package. Go find your custom package and just import your mouse orbit 2 script. That goes into a scripts folder. I'm going to tidy my physics engine script into there while we're at it. Mouse orbit 2 you can drag onto main camera. And if you look at main camera now, under the mouse orbit 2 component, you will see that it's asking for a target. We're going to make the ball the target. Now let's just play. Watch what happens. Now the ball is following, the camera's following the ball. The ball doesn't look like it's moving. Well, it isn't yet because we haven't given any velocity. But let's give it lots of velocity in a couple of different directions. The position's moving like crazy, but you can't see it moving. By the way, you can zoom in and out. So the slight modification I made to Unity's standard mouse orbit script is that you can zoom in and out with a mouse wheel. But look, this ball looks like it's doing absolutely nothing, and that's what things in deep space look like when they're hurtling along at high speed. You come alongside an asteroid or a probe or something like that, it doesn't look like it's doing anything when you're right next to it. And its movement relative to the background stars is insignificant, so it looks stationary, and that's exactly what we want. So that's fantastic. We now have a simple implementation of Newton's first law. What we need to do in the next video is to look at the forces on this ball, because what the actual interpretation says is unless acted on by an external force. I prefer to say unless acted on by an unbalanced external force. So what we're going to do next is to allow for forces on the ball and continue this same behavior if all the forces cancel out. Otherwise, we will panic, and then after that, we'll fix it with Newton's second law. Cool. So congratulations on getting this far. We're set up, and you have something that is simply moving through space.